Today we want to talk about privacy on the blockchain. And this is one of the issues that was actually mentioned in one of the homeworks in this course. So consider this scenario. Suppose that you're paying someone on the blockchain. So for example, Alice is paying some money to Bob. Now, we're going to imagine that this is the Ethereum blockchain, but what I'm saying here also applies to Bitcoin and all the other blockchains. So let's say that Alice creates a transaction and she pays Bob, let's say 1 Ether. Okay. Now, and let's call this transaction. So what's actually happening? Alice creates this transaction and announces this transaction to everyone on the network. It goes around the network using the gossip protocol, and then it gets picked up by a miner and added to a block, right? But this particular transaction is going to also include Alice's identity. Well, not the real world identity, but at least the blockchain identity. So it's going to contain Alice's address in the blockchain, which is basically her public key or the hash of her public key. So everyone on the blockchain sees that someone with this particular public key, with the public key of Alice, is actually making this transaction. But remember, everything on the blockchain is public, and everyone has reached a consensus about the history of transactions. So when Bob sees this transaction, he's not only seeing that he's being paid, he also sees that this is the public key of Alice. So he can go back and look into the history of all transactions and actually see all of Alice's previous transactions, right? So I can look into every block starting from the Genesis block, the very first block, and I can then go and look at every transaction and see if this particular public key was paid in that transaction, or if this particular public key was spending money in that transaction. So just by knowing one transaction from Alice, I can pretty much find the whole history of everything that she has done on the blockchain. And of course, this is terrible. We don't want to have this kind of thing. This is a violation of Alice's privacy. But this is not just something that Bob can do. You can imagine that all of the information that I'm talking about is public. So as soon as someone connects Alice's real-world identity to her public key, they can go and trace everything that has happened using this particular public key. And then they can know what exactly Alice has done in the past. Okay. So this is, of course, bad. But the other issue here is that it doesn't really help if Alice creates several different public keys. So we've talked about this point before. Anyone on the blockchain can create as many accounts as they like. So let's say Alice creates 5 or 500 or 5,000 different accounts. It doesn't really matter, because if I want to trace what Alice has done, as soon as I know one of her accounts, I can trace all of the flow of the money into this account and out of this. So if Alice was using, let's say, her first account and sending some money to her second account, I can see that transaction also on the blockchain. And I can very likely deduce that, well, if this account only has money coming from Alice, this is probably also Alice. This is just another alias of Alice, right? So just creating several different accounts and transferring money between them, and it does make it a little bit harder for other people to follow you on the blockchain, but it doesn't really provide you the kind of privacy that you would like to have. So this goes back to the problem in the homework where I asked you, how would you gain the actual privacy here? Now, some people in the homework actually had really interesting ideas. So there was this solution that said Alice would just sell all of her Bitcoin, get cash or get gold, some real world equivalent of money, and then she would again sell it to someone else and buy Bitcoin. And this second time, she will buy the Bitcoin using a new identity. So this will disconnect the two identities. Okay. Now that makes sense, But that's also not going to work all the time, and it's also very costly, and it depends on things outside of blockchain. So let's say, for example, I want to transfer money from my first public key to my second public key. And I want no one on the blockchain to be able to find out about this. I want no one on the blockchain to understand that these two are the public keys of the same person. Sure, I can just sell whatever money I have and convert it, let's say, to dollars. But who am I selling this to? I'm usually selling this to a real world company, right? So the person who's buying it from me would actually have the information. They would know that this public key belongs to me. They would be able to connect this public key to my real world identity. Okay, so this is what the broker knows. And sure, this is better than everyone knowing it, but it's still not private because there is one person or one company that knows this. And let's say that later on I use a different broker. So let's say this was broker one, and later on I use a different broker to buy Bitcoin or Ethereum again. And this is what broker two knows. Okay. Now, in some sense, now the two identities are disconnected from each other because I'm assuming that there is no one who knows both of my identities. So there is no one who knows that these two public keys belong to the same person. But what if these two collaborate with each other? Or what if one of them gets hacked and all of the information gets published? So let's say broker one gets hacked and everything that they knew was published, and broker two already knew this link. So after seeing the published data about broker one, they can now make this link as well. And then broker two would know that these two public keys both belong to me, right? Or you can also be more cynical and you can say, what if my government wants to spy on me? What if my government goes to both of these brokers and just forces them to hand out the information? So there are all sorts of problems like this, and we have to figure out how to really disconnect the two identities. So I want to send money from my first public key to my second public key, and I want to make sure that this is done in a way that really disconnects the two, so that no one else on the blockchain can figure out that these two public keys belong to the same person. Okay. Now, the technology that we're going to use, or the cryptographic primitive that we're going to use, is called a blind signature. So I want you to just remember the motivation that I told you about privacy on the blockchain, but let's now go to a completely different setting. I want to define the concept of blind signature, and then towards the end of this session, we will come back and talk about how to apply it to get privacy on the blockchain. Okay, what is a blind signature? A blind signature basically is a kind of signature where the signer doesn't know what they're signing. And again, this is one of those things that seems impossible, but we've seen in this course over and over again that there are many things that seem impossible but can actually be done in cryptography. So here's the idea. Let's say that Alice wants Bob to sign something. So Alice wants Bob to sign some message M. Okay. So let's say that we're using RSA signatures. So I can just assume that Bob already has announced his public key, but he also has a private key. So let me do this. Let's say this is Alice and this is Bob. So this is Alice, this is Bob. And Alice knows a message M, but this message M is private. It's something that she's not willing to share, and she doesn't want Bob to know the message M. Okay. Now, what does Bob have? Bob, let's say he's using RSA. So he has a private key and a public key. So he has a private key or a decryption key D or a signature key D, and he has a public key E. And this is public. And of course, let's say all of our calculations are modulo n in our RSA. So E and N are public. So you can assume that Alice knows E and N. Okay. Now, Alice wants to find Bob's signature on M. Okay, Alice wants Bob to sign M. So what is it that Alice actually wants? So Alice wants M to the power of D, right? Because remember the lecture on RSA, this is the signature of Bob on the message M. And again, all of my calculations are modulo n. So this is M to the power of D modulo n. Okay, this is what Alice wants to obtain. And let's say that Bob is willing to help. Let's say Bob is willing to give signatures. But Alice wants to get this signature without Bob finding out about M. So Bob shouldn't see M, but he should somehow sign it. Okay, this is the weird thing. So I want Alice to send a bunch of messages to Bob, and then I want Bob to reply to Alice, and then Alice should be able to calculate M to the power of D based on this interaction. Okay, now Alice cannot just send M to Bob, because if she just sends M to Bob, of course, Bob now knows M. So let's try this. This is the first attempt. Let's say that Alice takes the message M, and let's say she chooses some random number, for example, R. So Alice chooses a random R, and let's say she computes a new message, M prime, which is M times R. So just multiplies this random number by the actual message that she wants to see signed. And let's say that she sends this M prime to Bob, okay, and sends M prime to Bob. Okay. Now let's say Bob signs this. So Bob signs M prime and returns it to Alice. Okay, so I had this number R, and Alice sent M prime, which was M times R, to Bob. And then Bob sent a signature. Let's call that S prime because it's the signature on M prime. And the signature is just M prime to the power of D. Okay, so now Alice knows M prime to the power of D, but she wants M to the power of D. Okay, but what do I know about M prime to the power of D? This is the third part. Alice does some computation, so she knows M prime to the power of D. But M prime to the power of D is basically M times R, all of it to the power of D, which is MD times RD. Okay. And this MD part is the signature that she wants, but unfortunately, there is also this RD part, and she doesn't know how to get rid of this because she knows R, but she doesn't know R to the power of D, right? Because remember, D was the private key of Bob. Only Bob knows D. Alice doesn't know R to the D. So at this point, Alice gets stuck. She has some signature that is somehow related to the signature that she actually wants, but she cannot find the signature that she actually wants. Well, how can she solve this? Well, if I had R to the power of D, then I could just divide this by R to the power of D. So the next thing Alice can do is to send the value of R to Bob and then get a signature on R from Bob. So if I get a signature from Bob on the value of R, that signature is R to the power of D. And then I can divide the first signature by the second signature, and I would get a signature on the message that I was looking for. But the problem here is that if I send R to Bob, Bob knows M prime, and Bob also knows R. So Bob can just divide M prime by R, and he can find M. And again, remember, M was a secret. I didn't want Bob to know the message. I just wanted Bob to sign on the message without knowing it. So this first attempt has already failed here. Okay. But let's now change it a little bit. So this is now our second attempt. Look, the problem here is that I had to divide by something that I did not know. And this thing was R to the power of D. I only know R. Okay, so let's just do some sort of reverse engineering here. And let's say that I want to be able to divide by the thing that I know at the end. So instead of dividing by R to the power of D, I want to be able to divide just by R. So what does this mean? This means that when I look at my signature, the signature that I'm getting, this is my wish list. I don't want it to be M to the power of D times R to the power of D. I want it to just be M to the power of D times R. Because if this is the case, then I can just divide my signature by R and I will know a signature on the original message M. Okay, but at this point, I don't know how to achieve this. This is just wish list, right? So here's the thing. What do I know about R? So previously, I had R to the power of D. How can I get from R to the power of D to R? Well, remember that if you encrypt and then decrypt, or if you decrypt and then encrypt, or if you sign and then verify and then sign, so on, all of these things will give you the identity function. So all I'm saying is that R to the power of D times E is equal to R, right? And Alice knows E. So in order to get R here, I can try to get R to the power of D times E. This tells me that I want my message M prime, the thing that I'm sending to Bob to sign, to be in a format such that when he signs it, this is the signature that I get. Because if I get this signature, then I'm happy. And it's easy to see now that you can just do M times R to the power of E for M prime. Okay, because the signature is just raising to the power of D. So if I just cancel these out, it's M times R to the power of E. So now this is my second attempt. I say that Alice chooses a random number R, but the message M prime that he computes is actually not M times R, it's M times R to the power of E. So I'm choosing a random number R, and then I'm encrypting it using Bob's public key, and then I'm multiplying it by my original message. And I sent this M prime to Bob. Okay, so the only thing that happened here is that M prime is no longer M times R, it's M times R to the power of E. And now Bob signs M prime and returns it to Alice. So this is S prime, which is M prime to the power of D. So I know that this signature S prime is M prime to the power of D, which is M times R to the power of E, all of it to the power of D, which is MD times RD. Okay. But now remember that R to the power of DE is just R. So this is equal to M to the power of D times R. And M to the power of D was the signature that Alice was actually looking for. Okay. So she computes the signature she was actually looking for, which is, let's say, S, by just taking S prime and dividing it by R. And remember that division is the same as multiplying by the inverse. We have a modular multiplicative inverse. I can just multiply by that. Okay, so my S becomes S prime times R inverse, which is, since S prime is M to the power of D times R, this is M to the power of D times R inverse, which is just M to the power of D, which is exactly what I wanted. I wanted a signature on M, and M to the power of D is a signature on M. So after this happens, Alice can calculate S, which is m to the power of d. So this looks really weird, but I just want you to go over this again and make sure that you understand everything that is going on here. So Alice wants Bob's signature on the message M, and Bob is willing to cooperate here. So Bob is not trying to hide anything, but Alice is trying to hide M. So the way that she actually gets this signature is by first blinding the message, by first creating a different message, M prime. And the way this message was created was that Alice chose a random number R and encrypted it, got R to the power of E, and then multiplied that by M and sent this to Bob. And then Bob signs this new message. This is the signature that Bob returns to Alice, which is M prime to the power of D. And based on that, Alice can just divide this signature by R because Alice is the only one who knows R, and she can get M to the power of D. And it's also easy to go and verify that Bob can't get any information here with the same assumptions as in RSA. So as long as Bob cannot break RSA, he cannot know what Alice's original message M was. Okay. So there is a question here. Can Alice encrypt the message, get signed, and decrypt the message? So what do you mean? You mean that M prime is just M to the power of E? I didn't understand the question in the chat. Oh, I see. Okay. So the question is, Alice encrypts the message using some value, then gets it signed by Bob, and then she decrypts it. That doesn't actually work because if you have different pairs of keys, you cannot just apply them in any order. And the problem is that usually in the keys that you have different values of n, right? Because this n is something that Bob has chosen. Remember, if you go back to the whole lecture on RSA, the security of RSA was based on no one else being able to factorize this number n. So the way n is chosen is that n is the multiplication of two different two different prime numbers, and Bob is the one who has chosen those prime numbers, and those prime numbers are only known to Bob. So Alice cannot have a public key with the same n, because if that's the case, then Alice also knows how to find the prime factors of n, and then Alice can find d. Okay, so let me continue with this now. How can we use it? How can we use blind signatures? So I called this a second attempt, but actually this is called blind signatures. It's a blind signature in the sense that Bob doesn't know what he's signing. Okay, so here's one example use case. We can use this for voting. So suppose that a bunch of people want to go and cast a vote, but we don't want to know their votes, but at the same time, we want to make sure that everyone who's voting is actually allowed to vote. So how does this work in the real world? In the real world, you have some voting authority, let's say someone, let's call him Bob now. He's standing at a desk, and the way this works is that Alice goes to Bob, and usually there is like this voting slip where Alice can write her vote. So let's say she writes her vote, and then there is a piece of paper that covers the vote such that Bob cannot see it. But then Bob verifies Alice's signature, sorry, Bob verifies Alice's identity, and then he signs here, okay? And then later on, after Bob has signed, Alice can remove this blinder, can remove the thing that was over her vote. And now you have a vote that also has Bob's signature on it. And if we assume that any vote that has Bob's signature on it is valid, you can just drop this into the voting box and then it will be counted, right? So this is how we would do it in the real world. But how can I do it in this case on the blockchain, let's say? Well, again, the situation is very similar. It's just that Alice wants to vote. So Alice has this message M, and the message M is her vote. All she does is that she computes some M prime, which is a blinding of M, and then lets Bob sign that. Now, Bob wants to make sure that Alice can vote only once. So Bob tells Alice, I will sign for you exactly one message. Okay, so Bob tells Alice, I don't care how many different messages you have, and I don't care what I'm signing, but one vote, one signature. So you can just give me one message and I will sign whatever you give me, but only for once. Now, Alice can just take her vote, which is this M, blind it like this, give it to Bob, and then Bob signs it. And if we trust that Bob will not sign more than one vote for each voter, then Bob didn't know what or who Alice voted for, but Alice could get the signature of Bob on her vote, and so she can now prove that this is a valid vote. Okay, so this is one of the use cases. But the more interesting use case for us is, of course, gaining privacy on the blockchain. So remember, I have two different accounts. I have A1 and A2. I want to send money from A1 to A2, but I want to somehow make sure that no one knows that A1 and A2 belong to the same person. Now, to get to this point, I again want you to just imagine some non-blockchain scenario. So let's say that there is a central bank. So just consider this. Consider banking, let's say, with blind transactions. So what do I mean here? Let's say I have a bank. Oops. This is the bank. And many different people have accounts here. Okay, including Alice and Bob. And let's say that Alice wants to transfer some money to Bob. But we want to make sure that the bank does not know that it was actually Alice who paid Bob. So you can imagine that there are many different people who are making transactions. So I have, let's say, Alice 1, Bob 1, Alice 2, Bob 2, so on, and Alice N, Bob N. And let's say that all of these people have accounts with the bank. And let's say that in each case, Alice wants to transfer some amount of money to Bob. So let's say they all want to transfer $1. Okay. Now, I say they all want to transfer $1 because if you want to transfer multiples of $1, you can just consider that as several transfers of $1, right? So it's just $1 always going from Alice to Bob. Now, ideally, I want the bank to be able to process these transactions. So these transactions are all done using the bank accounts. So here, Alice's bank account balance should go down by $1 and Bob's balance should go up by $1. And here the same thing. But very importantly, I don't want the bank to know who's paying whom. So I want to make sure that the bank sees that, well, Bob 1, Bob 2 to Bob N, they have their balances increasing. So they're receiving some money. But I don't want the bank to know who's paying Bob 1. From bank's point of view, it should not be distinguishable if it is Alice 1 who's paying Bob 1, or it's Alice 2, or it's Alice N. Okay? To imagine this, just imagine how banknotes work in the real world. So if I have a banknote, if I have, let's say, a 10 Hong Kong dollar banknote. I can give it to you, and then you can go and deposit it into your bank account, right? And no one in the banking system would be able to know that I was the one who paid you, right? So if I want to transfer money from my bank account to your bank account, and I want the bank to not have a record of it, instead of doing a direct transfer, instead of doing, let's say, an FPS transfer, I can first go and withdraw banknotes from my bank. Then I give you the banknotes physically, and then you go to your bank and you deposit the banknotes. And this will just disconnect the link between us so that the bank doesn't know that it was me who paid you. Okay. But the problem with the real world banknotes is that they actually have serial numbers, right? And because they have serial numbers, if we do something like this, if let's say Alice goes and takes $1 banknote from the bank, that banknote has a serial number, and the bank can remember that I gave the banknote with serial number, let's say 1234 to Alice. And then later on, if Bob comes to the branch and deposits the same banknote, the bank knows that it was Alice who paid Bob. Now, maybe not directly, maybe Alice paid someone else and there were a bunch of other transactions before it ended up with Bob, but at least indirectly Alice paid Bob. And this is also a violation of privacy that I don't want to allow. So I don't want the bank to know where this banknote came from. Okay, how can we do this? Well, the way we can do this is by having serial numbers on our banknotes, but saying that the bank doesn't know the serial number. So this is my protocol, and I'm going to use blind signatures. In step 1, Alice creates a banknote. Now, this might be weird for you, but this is fine. We can do this. So Alice creates a banknote as a customer. And let's say this banknote is M, and it has to have a particular format. So, or sorry, it's B, and it has to have a particular format. So it can be something like this. This is a banknote with serial number and then a number. Okay, and this number should be long. Let's say this number has to be, I don't know, 256 bits. Okay, so Alice creates a banknote and she just chooses a random serial number. And this serial number is really long, so it's unlikely that two people choose the same serial number. And if you want to make it even more unlikely, you can just choose the serial number to be longer. So I don't know, 1024 bits. It doesn't really matter that much because even 256 gives us so many possibilities that in the real world, you will not have clashes of serial numbers. Okay. Now, I want to say that the banknote is valid only if the bank has signed it. So I say that the bank has, again, private key D, and it has a public key E, and all the calculations are modulo N. So the bank has published E and N, right? So everyone can verify bank signatures, including the bank itself, but only the bank can sign because you need D to sign. And a banknote is invalid if it doesn't have the bank signature. So Alice creates this banknote, and this is an invalid banknote because it doesn't have the bank signature. And let's say that I want to have the signatures on hashes. So I want my message M to be the hash of the banknote B. Okay. So when I say a signature on a banknote, I mean a signature on its hash, actually. So Alice wants to find the bank signature on this M so that B becomes a valid banknote. Okay. So we are going to use just the protocol that we've seen here, blind signatures. So in step 2, Alice chooses a random R and computes M prime. which, remember, this was just M times R to the power of E, and sends it to the bank. Okay, so Alice here is sending M prime to the bank. Now, the bank signs whatever Alice gives it, but every signature costs $1. So from the bank's point of view, this M prime is just some gibberish. It doesn't have any meaning. Because, I mean, to be honest, the way M prime was created was that we first took a hash of something that had a random serial number in it. So this hash is already gibberish. But then we also multiplied it by some other random number, R to the power of E. So this M prime really looks like garbage to the bank. But the bank doesn't care. The bank signs anything, but every signature costs $1. So when Alice sends this message M prime to the bank says, okay, I'll deduct $1 from your balance, and then I give you the signature on M prime. So this is step 3. The bank deducts $1 from Alice's balance and gives her the signature. Now, what is the signature? The signature is just M prime to the power of D. And now, just as we've seen before, Alice can calculate M to the power of D based on that. So this is step 4. Alice computes the signature on M to the power of D, based on what we've seen before, and sends these things to Bob. And sends Bob, well, I want to pay Bob, so I'm going to give Bob the banknote. And I'm also going to give Bob the signature, which is the signature on the hash of this banknote. So this already shows Bob that this is a valid banknote, okay? But as soon as I give this to Bob, Bob will deposit it with the bank. So Bob sends B and M to the power of D to the bank. Okay. And remember, all of these things are happening in parallel for many different pairs of Alices and Bobs. So many people are doing the same thing. So Alice sent M prime to the bank. The bank sent the signature on M prime to Alice. And then Alice sent the banknote and the signature on the banknote to Bob. And finally, Bob is sending the banknote and the signature on the banknote to the bank. Now, at this point, the bank can verify this signature, right? The bank can verify that this is a valid signature on the hash of this banknote. So the bank knows that this is actually a valid banknote that was taken out of the bank at some point, but the bank doesn't know which one of the banknotes it was. The bank doesn't know when Bob is coming here and depositing this banknote, is this the banknote that was taken out by Alice 1 or Alice 2 or Alice N or so on. So from the bank's point of view, the only thing that is verifiable is that I have my own signature on this banknote B. But I have never seen this banknote B before, so I don't know which withdrawal created this banknote. All I know is that this corresponds to one of the people who withdrew money from their accounts, but not which one again. Okay, so now the bank has to do some verifications. So let me actually write it here. I know this is not great, but I want you to see it here. So this is step 6. What should the bank check? The bank checks that the signature is valid. Okay. So that the MD is a valid signature of the bank itself on B, on the hash of B. Okay, this is the first check. But also, we have to stop double spending here, right? So Bob knows this particular banknote and signature on the banknote. So Bob can just deposit the same banknote several times. Or maybe Bob deposits this banknote and Alice also deposits the same banknote. Or maybe Alice gave the same banknote with the valid signature of the bank to many different people, to Bob and Carol and Charlie and so on, right? So we want to make sure that each one of the banknotes can be deposited only once. And this is actually why I had the serial number in the banknote. So the bank also keeps, let's say, a public list, or it can also be private. It doesn't really matter. So the bank remembers the serial numbers of spent transactions, of spent banknotes. So what are the serial numbers of all the banknotes that have already been deposited back into the bank? Okay, so here I have all of these serial numbers, and the bank just checks. It checks that I have not paid for the same serial number before. So this was the first check. The second check, the bank checks. Sorry, this banknote was small b. And this is also small b. The bank checks that the serial number on B is new. So the serial number of B was not deposited before. Okay. And if so, then the bank increases Bob's balance. So now you see that this is actually very interesting, because I had many different people who came to the bank and asked for signatures on many different banknotes that they had created. And by the way, a very important point here is that all the banknotes have the same value. All the banknotes are just worth $1, right? Otherwise, this wouldn't work. But I mean, of course, I can have different denominations of banknotes. I can have $1, $5, $20, and so on. And then I can say the bank has several pairs of keys, and the bank uses different keys to sign for different denominations. So you can do something like that. But for simplicity right now, let's say that all of the banknotes are $1 banknotes. So I had N different people who came and asked the bank for signatures, which were basically the same as saying that they were withdrawing $1 each from their accounts. And then they went and gave this $1 to other people. And then those people came back and deposited. So I had N withdrawals and N deposits. But as the bank, I don't know which withdrawal corresponded to which deposits. Right? So we have perfect privacy here, in the sense that, well, all I know about, let's say, Bob 2 is that he's depositing $1. So he should have gotten that $1 from one of the Alices, but I don't know which one. Okay. So this is how I'm getting the privacy. And by the way, from the point of view of Bob, because Bob doesn't trust Alice, when Alice gives Bob a banknote with a signature, Bob is not yet completely sure that this is a valid banknote, because maybe Alice has spent it before. So as soon as Bob receives this banknote, he will go to the bank and try to deposit it. And if Alice is buying something from Bob, Bob will not give the item to Alice until he deposits it successfully and sees that the bank has increased his bank balance, account balance. Yeah. Okay. So this is how we're doing banking with blind transactions. But now let's talk about how we can get privacy on the blockchain finally. And this is the concept of mixers. So what is a mixer? A mixer is a service where a lot of people can come and deposit money with the service, and then they can take out their money using a new identity. They can take out their money in new accounts. Okay. But the important point is that no one should be able to connect the previous accounts to the new accounts. But we've seen something like this here, right? So here I was saying that Alice 1 is paying Bob 1, but just imagine if Alice and Bob were the same people. So Alice 1 is the same as Bob 1, Alice 2 is the same as Bob 2. These are just different aliases. These are just different accounts of the same person. So Alice 1 is just paying to another account that also belongs to her. Okay. Now, if we do this kind of payment, and if we implement this bank as a smart contract, by the way, that's also really interesting. That's a problem that you have to think about. How can you implement this bank as a smart contract? It's actually doable, and it's actually very much related to your final project. Then I can have many different people who are depositing money with their first account, and then they're withdrawing the money with their second account, but no one can connect their first accounts to their second accounts. So this would ensure that their money is mixed up. So a mixer is a service in which, let's say, n people can each deposit the same amount of money. Deposit, let's say, 1 Ether in this case, and then receive it in new accounts. But no one can connect the deposits with the withdrawals. Okay, so no one knows which new account corresponds to which old account. But when I say no one, I have to actually say no one else, right? Because of course, if you're one of the people taking part in this mixing service, of course, you know your old account and your new account. Okay, but I want to make sure that no one else can connect the deposits and the withdrawals. I just want to add one last point for today's lecture, and that's about, again, double spending. So here we said that the Alice 1 gives the banknote to Bob, and we had a problem here, and the problem was that Bob didn't really trust Alice, and Bob was thinking, well, what if this banknote is already spent? What if Alice has given this banknote to someone else as well? So the only way that Bob had to really verify that this banknote is a valid banknote and it wasn't spent before was to go back to the bank and deposit it. But suppose that I cannot do this immediately. So suppose that I want to, for example, have an offline payment. So maybe Alice is giving this banknote to Bob, but Bob is not connected to the internet. Maybe, let's say, I don't know, Bob is a vending machine, has to give the item to Alice immediately, but it's currently not connected to the internet, cannot check with the bank whether this is a valid banknote. Can we make sure that Alice cannot actually double spend this money, that this money has to definitely go to Bob? And can we somehow embed Bob's identity into the banknote itself? And the answer is yes. So I can just change my banknote by saying that, well, previously my banknote was of this format. It was just saying this is a banknote with this serial number. But now I can say this is a banknote with this serial number. And then I can say that the only person who can deposit this banknote is Bob. Okay, so this is a banknote with this serial number payable to Bob. And I write Bob here, but this is actually going to be a public key, right? Or an account number. And if I do this, so my banknote will now have the serial number, which was long, and it's also going to have the name or the public key of the person who can use this banknote, and only that person can use the banknote. Okay, so again, I'm taking the hash, I'm doing the blind signature, blah, blah, and then I'm sending it to Bob. And when I send it to Bob, Bob can already check. If he sees his own public key in the banknote, he knows that no one else can possibly deposit this banknote. And if he knows the bank's public key, he can also verify that the banknote is correctly signed. So he can be sure that the only person who can deposit this banknote is Bob himself. And this ensures that no one can do double spending. Like, well, at least it ensures that Alice cannot use the same banknote to pay many different people. So it gives Bob the certainty that he can later on deposit with the bank and there would be no problem. And here I would just change the process for the bank to verify the identity as well. So other than the 2 checks that we had before, the bank also checks that the person who's depositing this banknote is actually the person that the banknote was payable to. Now, the metaphor you can use in this case is that now our banknotes are more like checks. But I guess for your generation, you haven't even seen checks. So probably banknotes make more sense.